we have thus finally come to this last exercise. If you were thinking about the first three, well, because we have already gone through the proofs of the results of this section and the first two exercises are about just that, so they have been solved. The third one I am not showing here because you can find it as a comment. Someone asked about it in the previous analysis video. So if you go there and see the comment, it's an answer to that comment. It's available there. So let's solve this one. So this one asks us to formulate proposition 11.10.7. That means our change of variables formula number 3. But when the function phi is monotonically decreasing, the original statement is for a monotonically increasing function. So let us first see the statement and then we will have to prove it. Let A and B be two real numbers such that A is less than B. Let phi from A comma B to phi B comma phi A. Because phi is supposed to be decreasing, so its range looks like this. The positions of A and B get interchanged. BA monotonically decreasing differentiable function such that its derivative phi prime is Riemann integrable. And we need another function, of course. Let f from phi of B comma phi of A to R be Riemann integrable. Alright, then what is the conclusion? Then this function minus of f composition phi times phi prime is Riemann integrable and its Riemann integral will be equal to the Riemann integral of f. So that minus sign comes, which is not there in the original proposition. And this integral equals the integral of f over the domain of f. Now we are going to prove this. Simply giving the statement, of course, is not enough. And in the proof, we are going to, in fact, use our original change of variables formula 3. So now we need to modify some things so that we can apply that formula here. We do not have an increasing phi now, we have a decreasing phi. Using this phi, however, we are going to define another function which will be increasing. So let us define that. Define a function psi from A comma B to psi a comma psi b by this rule, psi of x is defined to be equal to minus of phi of x. You can instantly see that because phi is decreasing, psi will be increasing. And similarly, using f, we are going to define another function. So let me not end the sentence here, and I cannot of course call it again f. Let me call it g. G will be defined from this into r, from psi a comma psi b to r by this rule, g of x equals f of minus x. Okay, then we can say some things about these two functions. The first thing of course is that both of them are well defined. I will just simply write whatever are true about these two functions. Some little verifications are needed to justify them, that I am going to leave to you. With the experience that by now you have with these things, you should be able to justify these little things yourself. Then psi and g are well defined. You know what to do to show that they are well defined. There is no absolute need to include that in the solution, but you should know yourself that whatever you have written is really, it's true. So what you do, say you want to show that psi is well defined. You take an input from this interval and show that that output, which of course is this, lies here in this range. The question of uniqueness of output is not really that much difficult, because psi has been defined in terms of phi, and phi gives us unique outputs, so obviously psi also get unique outputs. So this part you show. So that is just one thing. Then something else is also true about all these four functions, phi, psi, f and g, which is this: g composition psi is equal to f composition phi. It looks very nice, it's somewhat beautiful, and it's straightforward also. What you do, you just calculate this at any input x coming from your a comma b interval. You will see that when you apply the definitions of g and psi and you manipulate things, you will see that ultimately this is what you get. Okay, so this is another thing. What else is true? Psi is monotonically increasing. Okay, is differentiable. It is very easy to see why psi is differentiable, because psi is just the negative of another differentiable function phi. So obviously psi is differentiable, and in fact the derivative of psi is minus the derivative of phi, which is Riemann integrable. So psi prime is also Riemann integrable. Differentiable, and psi prime, which is minus phi prime, is Riemann integrable. Okay. Something else also we can say, which is about the function g. G is also Riemann integrable just like f. However, why? By which result? By the previous exercise. So we have to actually use exercise 3 here. and if you do that, you get this. So by exercise 11.10.3, you will see that the way we have defined G, that actually is how, whatever we have in this exercise. It's from this exercise that I got this idea of defining G like this. G is Riemann integrable, and what this exercise concludes is that the Riemann integral of G is actually equal to the Riemann integral of F. Integral of G over its domain is equal to integral of F over the domain of F. Alright, and now we are going to apply our original change of variables formula 3 to which functions? To G and psi, because psi now satisfies all those conditions, those hypotheses. Psi is monotonically increasing, is differentiable, and its derivative is Riemann integrable. But we also need G to be Riemann integrable, which however is coming from here. Okay, so we can apply our formula to G and psi. And what does the change of variables formula 3 say? What is its conclusion? It tells us that G composition psi times psi prime, this function is Riemann integrable, and its integral is equal to the integral of G. However, this composition is just F composition phi. So you can write F composition phi here, and in place of psi prime you have minus phi prime. So that's how you get that this integral is equal to this integral, which however is equal to this integral. So that's how you actually get your proof. So let me write the things. Also, by proposition 11.10, what was the number? 7 minus F composition phi times phi prime, which equals G composition psi times psi prime. In fact, we are talking about this function. It's just a fact that this is equal to this. This is Riemann integrable, and now we write the final conclusion. And its Riemann integral which is just this, is the integral of G. And that, of course, by this equality is the integral of F over the domain of F. and this is what you wanted to show. So that completes this exercise. It completes analysis 1. In fact, analysis 1 is over finally after so many days, so many months. So next week we can start, we will start analysis 2 with metric spaces. And tomorrow as usual we have our number theory upload. So that will be just all for today. So see you tomorrow. Until then, this is me, Lucifer from a mathematical room. Have a nice day.